Perfect. Okay. Welcome. So, when we started talking about diodes, I said there were three ways to look at a diode. We had the schematic symbol, we had the physical device, of which I got one right here. This is a 1N4001. This is the same one we used in the simulation. And then I drew this junction diagram, and I just said that this is a representation of the physics on the silicon. And so that's what we're going to go into today, so that we have an understanding of how these devices are constructed. And so we need to talk about what is a p-type material and what is an n-type material and what happens when you put the two together. Okay, now as we kind of know, silicon is what gets used predominantly for the semiconductor devices that we are dealing with. Okay, and so to answer the question of what is P and what is N, we're going to first start out with silicon. And silicon, how many valence electrons does silicon have? And remember, silicon, the valence electrons, I should say, the valence electrons are the electrons in the outermost orbit of the nucleus. And those valence electrons are what's moving around when we pass current through things, right? So the number of valence electrons a material has determines how conductive it is. So if we had one valence electron, we're looking at something like copper. That's a good conductor. And if you're looking at something that has 8 valence electrons, then you're looking at something like glass or rubber or plastic or things that are poor conductors, right? Things that don't conduct electricity. And if we get right in the center of this, we don't have one valence electron, and we don't have 8 valence electrons, then we have 4 valence electrons. We have something that is neither a good conductor nor a bad conductor, therefore it's a semiconductor. And the two most popular materials that are used to construct semiconductors are going to be germanium or silicon. Okay, those are kind of our two primary ones. Now, silicon ends up, I don't want to say it wins over germanium because each one of these is better at doing something different, but silicon ended up being the one that was easiest to construct massive, large amounts of circuits on one piece of silicon. So just because of the physics and the things you can do with silicon, it ends up winning out for the sake of making integrated circuits or making computer chips or digital logic chips. However you want to think about that. Okay, so we're going to be dealing with silicon, but what we say about silicon is applicable to germanium. Okay, and to talk about this semiconductor, we need to go ahead and look at our friend, the periodic table of elements, or at least some small subsection of the periodic table of elements. And if you're from a different country, they might refer to it as a Mendeleev chart. Mendeleev chart and periodic table of elements are the same thing. Mendeleev was the Russian scientist that actually started organizing the elements, and quite literally in a cabin in the middle of the woods, he noticed that the different weights associated with elements could be lined up, and it was actually the weight that could be used to organize this. So we give him credit where credit is due as a Mendeleev chart, or as we know in the US, a periodic table of elements. And if we go ahead and zoom in on one section, we have our group 14, we have our group 13, and our group 15. These are the only ones we're going to have to look at. Now, in each one of these groups, if you go vertically down the periodic table, they are organized such that our group 13 have 3 valence electrons. We refer to that as being trivalent. And silicon and germanium, our semiconductor substrate, what we construct our circuits, our semiconductors on, is in group 14, and it is tetravalent, it has 4 valence electrons. And in our group 15, we have stuff like phosphorus and others going down the list, but I've only focused on these because these are the ones that we're going to use for our examples. Our group 15 is pentavalent, or has 5 valence electrons. Okay, and now what ends up happening is, let's just take silicon, for example, silicon that has 4 valence electrons, and if we heat it up and we cool it at a very specific temperature, we control the cooling of this, we can actually get the silicon to form a crystalline lattice structure, a crystal. And the way it forms it is with these covalent bonds with the adjacent silicon. So over here, I've put up 5 silicon atoms, and this is a 2-dimensional representation of it, but this ends up being this 3-dimensional crystalline lattice structure, and it joins with these covalent bonds between the 4 valence electrons that silicon has with all the adjacent silicons. So all the silicon atoms are going to go ahead and form this bond with whatever's next to it, but specifically in this organization where they're sharing these electrons over here. They're sharing the valence electrons. Okay, and actually, let me see if I can pull up a 3-dimensional picture. Kind of nice sometimes being online, because I can very quickly do this. And let me see if I can do silicon crystalline lattice structure. Oh, look at that. Okay. It kind of looks like, well, actually, I think this might it's even, there we go. That's what the crystalline lattice structure looks like. Okay?
Looks like a 90s screensaver.
Hey, that's exactly what my screensaver looks like. Are you trying to say my screensaver's old? Yes, it does kind of look like a 90s screensaver. Okay, so what I showed previously was the 3-dimensional view, but it is useful for us to actually just look at it on a 2-dimensional view. Okay, so we go ahead, we heat up this vat of silicon, go to your local beach, pick up some sand, put it into a pot, heat it up. It's not that simple. It is actually quite difficult to control the cooling of it, and we can go ahead and create a silicon crystal, essentially. Okay. Now, the reason we care about those groups that were next to the silicon, and remember, we had something like boron in group 13 that had 3 valence electrons, and we had something like phosphorus in group 14 that had 5 valence electrons. We can add these 2 elements, whether it's boron in group 13 or phosphorus in group 15, we can add this element into the mix. And so we can take our silicon, and this process is actually called doping. We can take this impurity or this other element and we can add it to the silicon, and we're going to be able to create 2 different types of materials. Now, in this case, if we go ahead and take boron, boron has 3 valence electrons, and we add it to the mix of the silicon. If you notice, there's one spot that the other silicon adjacent to it is not able to form that covalent bond. And when we have the absence of an electron, we actually refer to this as a hole. So if we had silicon here, it'd be formed up and we wouldn't get this hole. But once we add the impurity of boron, which only has 3 valence electrons, into the mix of the silicon, we actually get this absence of an electron. Now, having a deficiency of this electron makes the material more positive, P. And so we refer to this material as P-type. So over here I've put a cross-sectional view of our silicon that has been doped with this impurity of boron. So over here on the substrate we have pure silicon in a crystalline lattice structure, and then through some process we've added this this impurity of boron to just this region of the silicon, and doing that has created a material that now has an absence of an electron, or a hole. The key word here is hole. And now we have this region that we will refer to as P-type. Now we can do the same thing in the other direction. We can take our crystalline lattice structure and we can go ahead and through some process add this impurity to the silicon, and in this case we're going to add phosphorus, and phosphorus is in that group 15, therefore it's pentavalent and it has 5 valence electrons. So in this case, by adding the phosphorus into the mix of the silicon, we've actually added 1 extra electron that is not bonded with anything. So this electron is free to move around. We have this extra electron. So now you should start thinking, well, if we, in one case we have the absence of an electron, we have a hole, and in the other case we have an extra electron, what are we doing to the electrical property of this material? We're actually making it more conductive, because this extra electron is not tied to anything. It is free to do whatever it does, and it is just 1 free electron, just like in the case of copper, where copper has 1 valence electron. That electron is free to move around. Well, so is this electron. Now in this case, since we've added 1 extra electron, and so now we have this material with a bunch of extra electrons floating around, we've made it more negative. And so we refer to that as an N-type material, okay? So the same thing with the cross-sectional area of a piece of silicon. I've doped it with this phosphorus, making this area or this region more negative. Okay, now how do you go ahead and do this? How do you add this impurity? There's a couple of different methods. There's ion bombardment, there's deposition, vapor deposition. You can go ahead and heat up the silicon. So after it's a crystal, you can heat it up, you can warm it up, and you can make it a little more receptive to like adding stuff into it. And then you can quite literally just add a gas of the phosphorus or the boron, and it'll settle into the silicon. So that's one technique for adding these impurities to the silicon. Okay, so we can have a P-type material which has an absence of an electron, which is a hole, and we can have an N-type material that is has 1 extra electron that makes it more negative. Okay, so kind of 2 sides of a coin. Now, let's talk about a property that each of these materials, the N-type and the P-type, actually have. So silicon by itself, if I had just the silicon crystalline lattice structure, just that chunk of silicon, it is not very conductive. A little bit, but not much. But once we add that, phosphorus in the case to add that extra electron to make it more negative, and we get that N-type material. We now have made that material much more conductive. And now if we go ahead and just took a chunk of N-type material and we attach it to a voltage source, we can actually push current through it, right? That one extra electron is free to propagate and move around. And so the conventional current, as we've been thinking this whole time, still goes in a clockwise fashion as I've drawn it here. But keep in mind that now that we're looking at the physics internal to the device, it makes sense to start looking at electron flow. So which way are the actual electrons moving? So the actual electrons, that free extra electron that we have, is free to move around. So if you think about it, these electrons can now pop and migrate and move. They once we apply a voltage to it, and they're going in this direction, right? They're just moving from one phosphorus to the next phosphorus to the next phosphorus. Let's start over. Oh, wow, my camera's mirrored. There, we'll do this, right? They're moving along. Okay, and so in this case, we refer to the electrons as being the majority carrier. They are responsible for the movement of charge. So we refer to that as a majority carrier. It is what is responsible for the movement of charge. Okay, now that's in the case of an N-type material. Now, the same thing actually does happen with a P-type material. However, there is a subtle but pretty big difference, which is that the electrons are not the majority carrier. The holes are the majority carrier. And I think this is the harder one to think about, because we're kind of used to electrons moving around and being responsible for doing the work. But if we have the absence of an electron, in other words, if we have a hole, that hole can do the same thing that an electron can. The hole, the absence of an electron, can actually move around. And so it's a little bit of an abstract concept to get your head around, but these holes can actually pop and move. And one analogy I like to think about is think about some water and having bubbles inside of that water, right? The absence of the water is free to move around. If you open, a can of Coke and it starts fizzing and you have this gas percolating and moving throughout your ice cold beverage, you have the absence of the fluid that's actually moving. The same thing is true in the case of this absence of an electron. This bubble is moving through it. And so we do have movement of charge. However, the charge carrier is actually the hole. And so we refer to the holes as being the majority carrier, because we still have movement of charge. It's just happening with the holes, the lack of the electrons for a P-type material. Okay. Are there any questions about that? Usually I get a couple of questions at this point. People don't like that the absence of something moves.
Can you show the process of the current and how it flows?
You know what? Maybe I can find a little animation of holes moving. Holes move. Sometimes Google search, you don't know what's gonna come up. Let's see. P-type holes moving. I would love to find an animation of this. I am finding, let's see, I found one picture. You know what? I don't really like this picture because they're using a circle without something in it and they're calling that the electron. Let me see if I can find something better. Okay, it's actually the one right above my head over here. Okay, so these holes are popping and making their way to the right while the electrons are filling in that void. Does that help? Usually I take silence as a yes. So over here, you have this circle, which is your hole, and then that is moving to the right. And this has been doped with boron, so it's 3 valence electrons for this boron, but it's surrounded by the silicon. Let me see, and I wish I would have done this before, looked for a video. So I'm gonna give this 30 seconds of searching. I have a couple of videos. Let's see if one of these. Of course, there's YouTube ads, and that always makes things rough. Okay, that's not bad.
Flows of holes. This is not in the notes. Conductor. So can you see that? Initially, the electron is here. Okay.
But question: can you hear that video?
Then this electron can jump out.
Is that video?
The jump out, it will go to
it?
the positive plate. Okay.
Yes.
Okay. You see, there are 2 plate here, positive plate and negative plate. So this is in this thing is inside an electric field. Okay. So the electron jump out, then it will go to the positive plate. So this is the flows of the electrons. No matter where the electron is, the electron here or here or here. So when it jump out, it will go to the positive plate. So it jump out, okay, and go to the positive
over here
plate.
on the left,
and then
you have
it
a
will
hole.
leave a hole here. The hole, it carry positive charge and it will attract electrons. It can attract electrons from the surroundings. Let's say it attract the electrons from here. Okay, so you see what happens here. Okay, so you see the electrons from here, move into this hole. When the electron move into this hole, it fill this hole, okay? Then the hole disappear. Okay? And when the electrons jump out from here, go here, okay? Then it will leave a hole here. So then you see the hole, initially the hole is here, okay? Then the hole move here, right? So initially the hole is here. Okay, let me show you again. Initially the hole is here. Okay, when the electrons from here jump to this hole. Okay, so then the hole move here. The electrons jump back to the hole to fill the hole, and the hole disappear. This is called the recombinations.
This is great. He can do my job for me.
Okay, recombinations. Okay. And then the hole won't stop here because it can attract electrons from other place, right? Okay. So then, let's say the electrons from here, okay, go inside here. Then the hole, now the hole come here already. Okay, the hole come here. And then, okay, again, the electrons from here go here. Okay, electrons from here go here. Then the hole is here already. So you see the hole is moving. The holes move from here to here. After that, it moves from here to here, and then move to here. Okay. So let's see how the hole move. Okay. So the process continue. You see the hole is keep on moving. Okay. So you see the hole move.
Okay, does that kind of convey the idea?
Yeah.
Perfect. Okay, cool.
Although
Yeah.
it's funny that we paid full tuition to watch YouTube.
Well, somebody kept asking me questions. What do you want me to do?
I'm just kidding. I'm just kidding.
Okay. So, for our N-type material, the electrons are the majority carrier. There is current flowing. And when we have holes, the holes are the majority carrier. And as you saw, the hole is moving and the electrons are filling in its place as that hole propagates along the material. And so we consider the holes to be the majority carrier. They are the ones that's free to move around, but we still get current flowing. That's the point here. Okay, so in both cases, we have made a material that is conductive, definitely more conductive than silicon on its own. Okay, we just need to apply a voltage so that we get current flowing, and we will get either electrons moving for our N-type material, or we get holes moving in the opposite direction for our P-type material. All right, what does this have to do? So, how do we make a diode? What we're actually going to do is we are going to put the P-type material and the N-type material right next to each other. And we're going to construct this on the piece of silicon. So this is how it's done. You start out with a substrate of silicon, you heat it up, you dope it, and you add in that you add in that phosphorus to make a more negative type material, an N-type material, and then you go ahead and you dope it again in this area with our, let's just say, boron, in order to make a more positive type material, or a P-type material. Now, when you do that, we're actually forming this junction between the two of them. That's why I referred to it as a PN junction. So the magic takes place right along this line where the P and the N meet. Now, all we need to do is make some wired connections, one to the P-type material and one to the N-type material, and between these 2 points, we get a diode that's been formed. Okay, and so if I go back from the cross-sectional area of the construction of our diode, now we get to that junction diagram that had the P and the N right next to each other. And so this line right here between the P and the N is this line over here between the P and the N. And just like I said, how this is where our diode is formed between these two conductive, we call them taps, between the P and the N. Again, this PN junction is representative of one side of this diode over here, and the other side, the cathode band side, over here on the N-type. Okay, now what have we just done? Well, let's go ahead and let's represent our holes since we have a bunch of holes in the p-type material and we have a bunch of free electrons in the n-type material, let's represent those with a bunch of little positive symbols for the p-type, and let's represent our free electrons as a bunch of minuses in our n-type. Now, if you think about the construction, I go through a process to make this, and I set it up such that I have the p-type and the n-type right next to each other, just like this. And so I bake this in my oven, and I go ahead and I open the door and I pull it out. After I've done my doping, after I've added those impurities to the silicon. And so once I pull this out of the oven and I let it just sit, notice my situation that I have going on. I have a bunch of holes that have positive charge, and I have a bunch of electrons that have a negative charge. What do you think they're going to do to each other? They're going to want to attract each other, right? Let's go back to that first day of 211. Basic law of charges, right? Opposites attract, like charges repel. You know, it's that thing you say about your relationships, right? Well, they're opposite, and opposites attract, right? So that's exactly what's going to take place over here. I have a bunch of absence of electrons that have a positive charge, essentially, and I have a bunch of extra electrons that are responsible for a negative charge, and these two are going to attract each other. In fact, what they're going to start doing is they're going to start swapping these holes and electrons. So I haven't attached a voltage to this. I haven't tried to push current through it. All I did was make the thing and pull it out of the oven. And this is what's going to start happen all on its own. I leave this just sitting on a desk, and these holes and electrons are going to start mingling in the center. And so the holes from the p-type material will start to attract and jump over to the n side, and some of these free electrons from the n side are going to jump over to the other side. So they start swapping charges a little bit, but at the center where they are closest to each other, okay? The ones in the back can't exactly jump all the way because they have all of this stuff in the way. And the same thing with the holes that are in the back over here. They're kind of furthest away. They're going to have trouble migrating over in that direction. But the ones right at that junction start doing a little swapping. And again, with no intervention on my part, I just constructed it and pulled it out of the oven. Now, what ends up happening is, once the little swapping takes place, I start to get my positive charge on this side, and I start to get my negative charge on this side. And what this starts to look like is a battery. It starts to look like an electric field is actually starting to form. And this electric field starts to form, and eventually it reaches this point where no more further charge can go ahead and swap. They're not going to all just jump over and cross, because as they start to do that, an electric field starts to form. That electric field is going to prevent the further mingling of these outer charges, these free holes and these free electrons. Okay, and so we get this electric field. We actually refer to this as a built-in electric field. It exists without us having to do anything. It's a feature of the construction of putting this p-type material right next to the other one. Okay, so it reaches a point of equilibrium. Now, what ends up happening is, in the center, our charges behave as though they're locked up. They're no longer really free to move, and we call this the depletion region. The depletion region, because it is depleted of free charge. Our free charge is all tied up in the construction of this little battery that's generating this electric field that doesn't allow any more mingling of our electrons or our holes. Okay, we still have free holes over here. Sorry, we still have free electrons over here, and we still have free holes over here, but they can't further jump over there because this barrier has been formed between the two. Okay, and we call this the depletion region, depleted of free charge. Now, this depletion region is what is responsible for that 0.7 volts that we need to exceed for this diode to conduct. So the reason we actually have to exceed 0.7 volts is because 0.7 volts is the voltage required to override this electric field and shrink the depletion region. Okay, so I am starting to get a little ahead of myself there. Let's go ahead and let's bias this diode. When I forward bias it, what I'm doing is I'm canceling out this electric field and I'm shrinking the depletion region. Okay, this is the big key. We are we are shrinking the area that is preventing our current from flowing. So once we go ahead and apply a voltage in the correct orientation, forward bias as we've learned it up till now, then this depletion region is going to start getting smaller. So when it was just sitting there before we applied our voltage, it was a large depletion region. Now, once we attach this voltage source and we overcome that built-in electric field, we actually start to allow the depletion region to get smaller. We force it to get smaller. And now we're starting to get to a point where we don't have a wall, we don't have a barrier in between our free electrons and our free holes. So now the free electrons are free to jump over the depletion region, and this will conduct. Okay, so just like we saw with our LED and with our diode when we looked at it in AC, when we apply the voltage in the correct orientation to forward bias it, we start to get current to flow. Well, this is what's happening on the inside. We are shrinking that depletion region, and now the free holes and the free electrons are free to move about their business and actually conduct electricity across that depletion region because we've made the depletion region very small. So eventually they can jump over. Okay, so at the end of the day, the depletion region shrinks and this will conduct current. But what happens when we reverse bias? So if we take that PN junction and we apply the voltage in kind of what we consider the incorrect direction, or the incorrect direction if you want to conduct current, then we have reverse biased our diode. And what we're actually doing is we are making the depletion region larger. So we're actually increasing the electric field. We are reinforcing that electric field. We are allowing more charge to get locked up in the center. And so this depletion region grows much larger. And the larger the depletion region is, the harder or more impossible it is to get current to actually flow. So in this case, current cannot flow. We are reverse biased, right? Okay. Now, everything that we kind of talked about with reference to diodes and our PN junction can actually be summed up in what's referred to as the diode characteristic curve. And so in the y-axis, I'm listing current, current flowing through our diode. And along the x-axis, I am listing our voltage. And so as we increase voltage in the forward bias direction, at some point, and this would be about 0.7 volts for that 1N4001 diode, which is constructed with silicon, we start to get conduction. So this right here is where our depletion region has shrunk sufficiently enough to get current to move through our diode. And so that depletion region is what's responsible for creating that barrier voltage that we must overcome. Barrier voltage and forward voltage are essentially the same thing. We just use barrier voltage when we're talking about the voltage required to shrink the depletion region on the actual silicon. But when we're talking about just a diode, the component, and we're not looking into the physics of it or anything, that's when it turns into being referred to as the forward voltage, but they are the same thing. The barrier voltage is what's responsible for the forward voltage. And so we need to exceed 0.7 volts in order to shrink that depletion region, get current to conduct. And once that depletion region gets small, you can see that we get to a point where it's just like almost like there's no resistance in there. That depletion region doesn't just change from not allowing current to all of a sudden being a closed switch. It happens gradually over time once we've gotten to that forward voltage and start to get above it. So once we get above the 0.7 volts, all of a sudden we get to this point where there's almost no resistance. And Ohm's law says when we have almost no resistance, we should get a lot of current flowing through it. And so that's why we get this almost vertical line here where all of a sudden current just goes through the roof, and that occurs after we've exceeded that barrier voltage. This is all in the forward biased direction, but if we go ahead and flip our diode or flip the voltage that we're applying to said diode, then you can think of that as being a negative voltage in this case, and all of this is reverse biased. Okay, so we should get no current flow in this direction. Now, this is not to scale. If this was to scale, this would actually be going through my room into the next room and be on a whiteboard over there. This breakdown of voltage actually occurs at many tens of volts in the reverse bias direction. So you can't, the diode is not just going to infinitely not allow current to flow through it. At some point, I'm applying too many volts, and I'm pushing those electrons so hard that eventually the diode is going to start to break down. And when that diode breaks down, we actually get, this is called avalanche current. And the reason they call it avalanche current is because the diode only permits like a few electrons to start moving, or if you're in the P side area, a few holes to propagate. But our depletion region at this point is huge. It's as big as it's going to get, but we're still increasing that voltage in the reverse bias direction, and we're saying we don't care if you can't conduct. We're going to make you conduct. And eventually things start to break down, and you can start to squeeze an electron, a hole, one at a time, little by little, and it picks up speed at that point. And that's why they call it avalanche. You can kind of think of it as like a snowball rolling down a hill. You start off with just a few majority carriers, but eventually it starts to get a lot more flowing through it. At that point, your diode is breaking down. It's hurting. You can actually do avalanche safely for a little bit, But eventually your diode just burns out. Very similar to what we did to that LED where we blew it up on the first day. Okay, so this is the characteristic curve. And for any diode, you have a characteristic curve. And if you wanted to know the specifics for like a 1N4001, you could go ahead and look up the characteristic curve. And they're all going to look just like this. It's just this breakdown voltage may be at 60 volts, it may be at 100 volts, it may be at 40 volts, depending on the diode you're using. And this forward voltage is also going to change this point that we start to conduct. If you're using germanium, expect a forward voltage of about 0.3 volts. If you're using silicon, expect it to be around 0.7 volts. And again, these diodes are kind of created for different purposes, different applications. So sometimes having a lower forward voltage is better. Sometimes having a higher forward voltage, but being able to have a higher breakdown voltage ends up being advantageous. So just depending on what your application is, some diodes are better suited for others. Also, there's something called the recovery time, which is how fast a diode can switch between the on and off. And that's also another feature that some diodes like a Schottky diode has a very fast recovery rate. It can actually swap between conducting and not conducting much quicker than your rectifier diodes that we've been looking at, the 1N4001. Okay? So and in fact, I do have actually a better image. I probably should have used this one instead. That actually kind of depicts what's going on here. If we've applied no voltage, we have the built-in depletion region. Once we get close to that forward voltage, that barrier voltage, and further exceed it, then we have a very small depletion region. And now the electrons in the holes can move. Our majority carriers can carry that current from one side to the other. And if we're reverse biased, we have that large depletion region. And then here is where we go ahead and we're just breaking the diode. We're going in the wrong direction. Eventually this diode will burn out. It is reverse biased to a point. It starts to avalanche and then it just breaks down. Oh, and here is another thermal breakdown is when you have too much power being dissipated by your diode, and that's what occurs if you don't use a current limiting resistor. So if we don't have a current limiting resistor to limit the current through it, you can see that as current jumps and starts going through the roof in this direction, that 0.7 volt drop stays the same across the diode, and power is equal to voltage times current. Therefore, power starts to go through the roof as well, and that's where you get your thermal breakdown. That's what we did with the LED, where it just started to get really bright, turned orange, and broke down on us. So I don't plan on actually scanning these and uploading them. There's a video. You're free to copy them from the video. I think I just have too much on my plate right now with 4 classes, 1 new prep, and posting videos and everything. So yeah, just watch the video again. Okay. So with that being said, I'm done with lecturing for today. Let's go ahead, take a 10-15 minute break. So right now it's 8, actually 9. So let's be back here at 9:15. I'm gonna walk through our next lab, and I'll do it on the bench with the multimeter, and we're all just gonna follow along with that. Okay. So I'll go ahead and I'll see you in 15, so at 9:15. All right. Thanks, everyone. Okay, so for this lab 1 part 3, we're going to go ahead and step through the lab document. So the first thing that it's asking us to do is to set the digital multimeter DMM to the diode test position. Now I have a multimeter on my bench, and we're going to set it to the diode test position, connect the diode to the DMM with the negative lead to the cathode and the positive lead to the anode. Okay, negative lead to the cathode and positive lead to the anode. Let me see if I can set these up side by side. Where is... Okay. It's going to get kind of small there. Okay. So we set the DMM to the diode test position. Now, what is that? Okay. Any decent quality multimeter has a diode test position. And on the X-Tech, this is the low cost one that I have listed on my multimeter page. I updated that yesterday, and so I had some couple of old options on there. It's been refreshed, and I list out what I think are good multimeters. If you don't have a multimeter, you should get one. You're going to use it at some point, either here or in the future. But any decent multimeter should have a diode test position. And you can see that right here. Now, this function is shared. So if I turn it to it, that little speaker symbol refers to measuring continuity. So to check if two things are connected to each other, the continuity measurement should generate a beep when we're below, usually like 3 ohms or less is considered to be conducting. And so you can hear it beeping right now. But this function is also on this specific multimeter shared with the diode test position. Okay, and here we have a diode, and let me go ahead and keep the orientation such that we have the cathode band on the right side. It doesn't look too great. Let's switch over to marker. Okay, so I have everything lined up as it should be. All of those are in the same orientation. And in fact, this is that other type of diode, a signal diode, a 1N4148. This one up here is actually constructed with germanium, and it has some different properties. But this is our 1N4001. Okay, so it's asking us set the DMM to the diode position. We've already done that. Connect the diode to the DMM with the negative lead to the cathode. Negative lead, I currently have that set up as my black one. And my positive lead to the anode. So we're going to hook it up like this and record the DMM reading, okay? So looks like we're reading 0.575, and that reading is in volts. This actually is the forward voltage. Okay, so the forward voltage for a good diode, V sub F, or V forward, is equal to 0.577. Okay, so write down 0.577 for that first one. Okay, and for a good diode, the forward DMM reading is relatively high or low? Okay, now here's my disclaimer. This lab I took from a workbook. I'm not the biggest fan of how some of these questions are listed, but I do like the overall procedure. So for a good diode, the forward DMM reading is relatively, let's go ahead and say low. Okay, so the better the diode is, the smaller that forward voltage is. Let me go ahead and get that out of the way. Okay, because if we had a perfect diode, it's going to act like a closed switch. That forward voltage should be low, should be 0 for an ideal diode. This is not an ideal diode. It is a less than ideal diode. It's a real diode. And so we don't have a 0 volt forward voltage, but we have a 0.577 volt forward voltage in this specific case. And that is relatively low in the grand scheme of things. Okay, so for a good diode, the forward DMM reading is relatively low. Okay, and we figured that out with the diode test function of this multimeter. Okay, now it goes ahead and asks us in number 2, switch the leads to the diode so that the negative lead of the DMM is connected to the anode and the positive lead to the cathode, and record the DMM reading. So over here, we want the negative, so this black one, to be connected to the anode and the positive to the cathode. So I'm going to go ahead and unclip that. Okay, and now essentially we get no measurement coming from our multimeter. It's as if the diode isn't even there. If I don't have my diode connected, I'm showing a 1, which is a 1 is the same as having an infinite number of ohms. And if it is connected, again, nothing changes. So this diode in this orientation is not conducting. Okay, so the reverse voltage for a good diode, V, is 0. Okay. Well, let's see, reverse voltage. See, and this is where I don't really care for the way some of these questions are written. Reverse voltage for a good diode. V reverse just write high. High will work for that. And for a good diode, the reverse DMM reading is relatively high. Okay, so both of these you can just list as high. All right. So that takes care of the diode test function that we have built into our multimeter. Every multimeter has this, or I should say any good multimeter. If I pull out my better multimeter over here, notice the diode function is all on its own, whereas the continuity measure is in a different position. So each multimeter has a different selection for how you get to that function. Okay, so that takes care of that. Let's go on to number 3. Connect the initial circuit as shown in figure 6.1-2. Okay, 6.1-2 is this one up here. And it's asking to apply a voltage through the diode and through this 1K resistor back to the minus. And the voltage is going to be, I believe, 5 volts. Where does it say that? If you find what the voltage is on the paper, let me know in chat. I'm looking for it right now. It is listed. Number 4. Okay, cool. Okay. So it's going to be 5 volts. So I'm going to go ahead and set up my voltage source to be 5 volts. Do that, I'm going to go ahead and use some test leads from my benchtop power supply. And I'm not going to turn it on just yet. But this is going to be my voltage source. So I will get 5 volts there. But we need to hook up that circuit, 61-2. So to do that, I'm going to take a breadboard. I got some other stuff going on this breadboard on the side. Don't pay any attention to those. And we're going to hook up. And I always advocate when you're doing this, try to make the breadboard look like your schematic. It just makes life easier. So I'm going to hook it up like 61-2. And that means I'm going to put the cathode side, the marking over here, facing to the right. Okay, so the white band I have placed right here. That's the cathode on this side. And then I'm going to put a 1K resistor going directly down to another unused group of 4 over here. But I'm going to make one side of the resistor connected to this diode side, to the cathode. Okay, so I'm going to need a 1K resistor. Now, a 1K resistor is 1,000 ohms. And if I'm looking for a 3-color band resistor, it's going to be brown, black, brown is 1, black is 0, and that last color is going to be for 2 zeros, our multiplier, which is going to be 2, so red. And that should give us 1K. So I'm looking for a brown, black, red. And here we got one. Okay, a little hard to see the color there, but reading from left to right, I have brown, black, and then red. That last color over here is the tolerance. This is a 5% tolerance resistor. And if we're ever unsure about reading the resistors, especially when you get into those 4 banded colored resistors, just test it with your multimeter. So I'm going to go ahead and verify this. I'm going to select the range. It should be in the 1K range. So let's put it over here at the 20K range so that I get 2 decimal points of precision and 2 decimal points in the K range. And I'm reading 0.99K, okay? So 0.99K that's exactly 1K for all practical purposes. Now, I'll take this to note something about the difference between an auto-ranging multimeter and a non-auto-ranging multimeter. So this right here is a non-auto-ranging multimeter, which means I need to guess at what the value is before I go ahead and just start taking measurements. So if I put this over into the mega ohm range, I'm not going to get a very accurate measurement. In fact, it can't, because this isn't a mega ohm resistance. And similarly, if I move this over into the 200 ohm range, again, I'm not going to get a measurement. But if I put it into the 2 kilo ohm range, I lose that most significant digit, and now I get 0.995K. And so that is 1K, except we now have an extra digit of precision than what I had before. So this is a non-auto ranging multimeter, and so I have to make some educated guesses as I use it. Now, if I have a ranging multimeter, so let me move that off and let me bring in my nice multimeter over here. Let's set this to ohms, and I don't have to worry about setting that range. And I can go ahead and measure this resistor. Now, the most accurate way to measure a resistor is without having your fingers on the conductors. Because your body has resistance, you're going to add that resistance in parallel with the resistance. So I don't want to do this. This is not a very good accurate way to take the measurement. And if you notice, I'm getting 0.992. A better way would be, at the very least, I only touch one side, and then the other side, I brace it against something like the table and take the measurement that way. And this multimeter is actually more accurate than my previous multimeter. So my previous multimeter said 0.995. It's actually 0.993. Okay, so just a word about multimeter usage and proper measurements. Now, if you notice, I didn't have to select any ranges. That was super easy and nice to take the measurement without me having to fiddle around with 4 different points of precision to get the correct range, get my multimeter within range of the resistance. Now, you can get an auto-ranging multimeter for much less than this multimeter. This multimeter is a $100 multimeter. This is my $23 budget multimeter that I think is very good quality for what it is. Even though it's non-auto ranging, it's very precise and accurate. It's very durable. This is a good multimeter that'll last a lifetime. Now, I do have, and I don't mind spending the time, for my $100 workbench challenge sessions that I'm doing, when I get to power supplies, I'm also going to cover multimeters. And so I wanted to find a budget multimeter in the $20 range that was auto ranging, and I wanted to find just the best one for 20 bucks. And so I came across this overseas unit, which is by a brand called Crenova or something like that, the MS8825, something like that. It's actually on my multimeter page, so you can see kind of a, not really a comparison, but I list all the options that I think are good options for the money. And so I found this guy, and I wouldn't mind taking a measurement with this. Now, here's actually my favorite thing about this overseas multimeter. It comes with 2 sets of probes. If you saw my clip leads on my cheap multimeter and you were jealous, you can get it with this multimeter for 20 bucks. And so it comes with 2 sets of probes. One, you know, kind of adequate quality. These aren't the highest quality probes, but they're not junk. And the same with these, except it also has the alligator clips, which is super convenient for taking measurements, or if you're measuring current and you just want to leave it in the circuit. So I'm going to use these clip leads, and let's go ahead and take a resistance measurement here, an ohm measurement. I'm going to put that in. So I went ahead and connected the positive over to here, and a little hard to see, but this is measuring volts, ohms, hertz, diode, milliamps, and microamps. So I want to make sure my red probe is in this position and my black probe's in the common position. And let's switch this over to ohms. And what's kind of nice is this is auto ranging. So I should hopefully get a reasonable value, and we can compare the accuracy of this one to my $100 multimeter. .994. So my $23 X-Tech non-auto ranging gave us 0.995. My higher quality was calibrated at one point. $100 multimeter gave us 0.993, and this one is actually giving us a resistance right in between the two, 0.994. So thus far, this guy seems to be plenty accurate for average use. The build quality is decent. I really don't have any complaints. It comes with 2 sets of probes, 1 clip lead and 1 regular normal probes, and it's 20 bucks on Amazon shipped. I'm really digging this one, the MS8233D. And in fact, I'm going to be, when I do the session, I have some precision voltage references as well as some precision resistances and precision currents, and we can actually compare the 3 of these multimeters and really find out how good is this MS8223. Okay, so a little bit sidetracked, but we have a 1K resistance. Let's use it in our circuit. By the way, I know I said this, I'll say it again. I really love that it comes with 2 sets of leads. If you break one, you have another set, and you have the difference between probing and clipping, which is brilliant. When you think about measuring current, you have to hold that. If you've done that in 211, and it's a pain in the butt. You got to dedicate one person to holding the probes for taking the current measurement, where you can just clip this on there and clip it to another one. Now, if you already have a multimeter, there's nothing wrong with having 2. 2 multimeters is always good, because half of the time I need to measure current and voltage at the same time. So having 2 multimeters is fantastic too. Not to mention, if you're ever wondering if one of your multimeters is acting up, you have a second multimeter to verify that that first one is, or they can verify each other, so to speak. Okay, but I'm going to stick to using my X-Tech. Okay, we're going to go ahead, hook it up just like in this circuit over here. We're going to put this 1K, just going to bend the leads. And now we have one side of this 1K connected to the cathode, and the other side needs to get connected to our positive from our voltage, and the resistor needs to connect to the negative. Okay, so I have my circuit now. I just need to turn on my power supply. Is my voice cutting off, or? Okay, perfect. Okay, so let's go ahead and move on to the next part. Okay, apply 5 volts to the circuit with the anode connected to the positive side of the source. Determine the circuit current from VR for the forward bias diode. Okay, so we want to measure the voltage drop across the resistance and infer the current. Is that what they're asking for? Apply 5 volts to the circuit with the anode connected to the positive side of the source. Determine the circuit current from V sub R. Ah, okay. So we had measured that forward current previously. What was the value? It was 0.5 something. Someone who wrote it down.
0.577.
0.577. Okay, so we're going to go ahead and take a voltage measurement across the resistor with 5 volts connected to it. Now, you'll see why I have several multimeters, and I just keep different types of leads attached to different ones depending on what I want to do. So I'm going to go ahead and set up this multimeter to voltage, and we're going to flip on power. And let's check what our voltage applied is first. Make sure that we are at least 5 volts. And the easiest way to measure, especially when you're measuring voltage, is just to insert the probe between where the lead inserts into the breadboard and then slightly push down with a little bit of pressure. That's going to give you a pretty good reading and a good contact over there so that we get an accurate measurement. I'm going to do the same thing on the bottom side of the resistor where the negative lead from the power supply is, and it looks like we're at 4.97. Okay, so not exactly 5 volts, but pretty close. If I wanted to, I could adjust this. Come on. All right. Actually, what's going to be better is All right, let's use my precision benchtop power supply. Now we're in any world, this is 5 volts. Okay, and that'll just make doing our calculation a little easier. Now we want to go ahead and take a measurement of V sub R. For the current going through the diode. Okay, so let's go ahead and take our measurement here. Again, I'm just going to push down into the breadboard, and I get 4.3, let's call that 4.34. Okay, we need to calculate current for this entire circuit. Pretty good 5 volts going through it. V sub R equals 4.34. V sub D equals 0.577. And R, we measured it, it was 1K. Okay, 0.994. I'm just going to go with 1K. Okay, now we can go ahead, calculate the current. I is going to be equal to 5 volts. Kirchhoff's voltage law, we just subtract from that the forward voltage that we measured, minus 0.577. Apply Ohm's law by dividing it by 1K, and we should get I. So I will do 5 minus 0.577 divided by 1K. 4.4 milliamps. Okay, so we got 4.4. I should have just written it right here. Okay, that's the answer to that one. However, I would not mind actually connecting up my multimeter and seeing what the measured current is through it and see that it actually is indeed 4.4 milliamps. I'm going to set this multimeter into my milliamp range. I know it is safely 4.4 milliamps. I have very strong encouragement that I am well below my 250 milliamp max. Actually, my max for this multimeter is 200 milliamps. Don't ever go above this, you'll blow the fuse. And so in the milliamp range, I can get an accurate current measurement. So I cut the circuit. I'm going to do it on the negative terminal. I'm going to clip that to my multimeter and put my multimeter in series. 4.3. 4.3 is pretty close to 4.4. So that's with this budget multimeter. Okay, let's go ahead and let's look at another multimeter. I'm going to set this one to milliamps. Now for this one to go to the milliamp range, I actually need to change the position of the lead. And it's beeping at me going, you're not in milliamp mode. Okay, now we are. I'm going to take my minus. No, that's not right. I'm going to take my minus, clip that onto my probe. And 4.3. Okay, here's one of the reasons I actually like that X-Tech because for 23 bucks, it's been matching my $100 multimeter consistently, and it has for years. So, you know, when you have something that's been producing good results for a number of years and is durable, you tend to go with it. So X-Tech and Amprobe are both multimeters within that are more along the lines of budget, and they produce good results consistently. Okay, so on the bench, we're measuring 4.3. Why are we not measuring 4.4? Well, for one thing, 0.1 milliamps or 100 microamps is quite a small measurement, and we're really optimized for taking measurements in the milliamp range. So both of these multimeters are going to be a little off the lower the current is. Also, I have long wires going everywhere. So these longer wires tend to have a little bit of resistance in them too. Okay, so independently verified 4.4 milliamps is good. Okay, next. Okay, yeah, for a good diode, wait, sorry, we are here. I equals 4.4. Is the diode conducting with the anode positive with respect to the cathode? Yes, the diode is conducting. The voltage drop across the forward bias diode is approximately, well, it should be 0.577. Let's double check that. I'm going to switch to voltage. Oh, there we are. This is why. 0.663. That's why we calculated 4.4 milliamps, but we calculated 4.4 milliamps using the forward voltage that we found in the previous step. But it turns out when we're applying 5 volts to the diode, we actually get a slightly higher forward voltage drop. It looks like we're at 0.66. So when we're using 5 volts to power the circuit as opposed to our multimeter taking the measurement, we get a 0.65, much closer to that second approximation that we do on the board. Okay, so 0.66. So I'm willing to bet that if we redid that calculation using 0.66 as opposed to 0.577, we're going to actually be at 4.3 milliamps instead of the 4.4 milliamps. Okay, so 0.665 for funsies. I'm going to do that again. Yeah, I said funsies. Okay, it was 5 minus 0.667 divided by 1,000. Hey, 4.3 milliamps. Perfect. Okay, so actually, both of these multimeters flawlessly measured the current going through it. So that's exciting. Okay, so why buy a $100 multimeter when a $23 multimeter will do the job? Okay, so is the diode conducting with the anode positive with respect to the cathode? Yes. The voltage drop across the forward bias diode is approximately 0.667. Turn the diode around so the positive side of the source will be connected to the cathode. Oh, we are flipping this around. It looks like we're going to be reverse biased. Okay, I just flipped the diode around. The cathode is now on this side. The anode's on this side. And I'm going to connect my 5 volt precision voltage source there. Apply 5 volts to the circuit. Determine the circuit current for V sub R. Determine the circuit current for... See, Again, this is the way this is written. The circuit current for the voltage drop across the resistor? Okay, so determine the circuit current for the reverse bias diode. What do you think it's going to be? I sent that to the wrong person. Okay, reverse bias diode, what should the current be through this circuit? Zero, right? Okay, so let's go ahead and let's actually measure that current. I'm just going to measure it this time. It's zero. It should be zero. It's reverse biased. It's not conducting. It's not allowing any current to flow through it. So, for number 6, I equals 0 milliamps. Is the diode conducting with the cathode positive with respect to the anode? No. It is not conducting. For the reverse bias condition, the diode is acting like an open circuit. It's not conducting. The resistance of the reverse bias diode is virtually, what is the resistance for an open anything? Infinite. It should have infinite resistance. If it is truly open and not conducting in any way, shape, or form, it should have as much resistance to those electrons as possible. Okay, that takes care of 6. Turn the diode around once more in order to forward bias it, then increase VA in small steps as indicated in the observation section, and note the current at each step. Okay. This is going to be easy with a variable voltage source. Okay, we're going to start at 0.5. And we've actually kind of already did this. We did this with the LED.
Professor, I have a question.
Yeah, what's up?
I know we went already past it, but we changed the voltage, the forward voltage from 0.57 to 0.667.
Yes, I did. I did that calculation twice. I did it once. The paper had you do it with the forward voltage that you found with the diode measurement of your multimeter. However, to get a more precise and accurate depiction of what's going on, I then changed it to 0.667 because that's what I measured in the circuit.
But we can stay with 0.577, right?
You can, yeah, for sure. Turn in whatever you want.
Okay.
Okay. So, we want to see the voltage applied, and then we want to see the current through it. I'm going to set up 2 multimeters. Perfect example. This is why you want 2 of them. Or you want 2 responsible lab partners that bring their multimeters to class, and that way when one screws up, you still have 2 multimeters if you have 3 partners, right? So I'm going to use my amp probe to do the current measurement. And I'm going to use the X-Tech to do the voltage measurement. My amp probe multimeter has a little more precision in the milliamp range. Okay, and the way I'm going to do this, I'm going to connect the black probe of the current measurement to the power supply on the negative terminal. I'm going to leave that underneath there. Then I'm going to take also a measurement of the applied voltage. So I'm going to switch my X-Tech over to voltage. I'm going to also clip on my voltage measurement to the negative side, because I'm going to be measuring between the negative and the positive for the applied voltage, and then I'll adjust my power supply till it reads the voltage we're interested in. And then we'll measure the current on the second multimeter as the current goes from the resistor through the amp probe back to the negative supply. I need one more cable to finish that up. So I'm going to take one of these leads, clip it onto my probe. Okay, so now the current is flowing through the resistor, through the yellow wire, through my amp probe multimeter, back to ground. The applied voltage is going to the incorrectly biased diode. I need to change that. Okay, and now we have everything we need. Okay, so for 0.5 volts, the current flowing through this is 0.04 or 0 milliamps. Either is correct. Okay, so that's for VA is equal to 0.5, I equals 0. Okay, let's bump that up to 1 volt. Okay, that's 1 volt exactly. And we are getting 0.43 milliamps. Okay, so for V sub A equal to 1 volt, I is equal to 0.43. Let's go up to 2 volts. Okay, for 2 volts, the current is 1.36 milliamps. Okay, 1.36 milliamps. Let's take that up to 3 volts. So you can see at this point, the diode is beginning to conduct. As it should, because we've exceeded that forward voltage. Now it's conducting even more. We're getting 2.34 milliamps with 3 volts applied. Let's take that up to 4 volts. And you get 3.32 milliamps. Okay, that's for 4 volts. Let's take that up to 5 volts. Okay, 5 volts applied, we get 4.3 milliamps. Let's take that up to 6 volts. We get 5.28 milliamps. Let's take that up to 6 volts. Sorry, take that up to 7 volts. 6.27 milliamps. 8 volts, 7.27 milliamps. Let's take that up to 9. With 9 volts, 8.26 milliamps. And let's take that up to 10. 9.26 milliamps. Okay, so at this point, the diode should be fully conducting, and the only component that's actually restricting the current or resisting in this case would be that resistor. So that's the only guy that's limiting the current through this series circuit at that point. Okay. So conclusion. Let's go back to the lab document. As VA was increased, the current increased. We can deduce, therefore, that diode conduction is directly proportional to V sub A when forward biased. What is the approximate DC resistance of the diode when VA is 7 volts? Okay, what is the approximate DC resistance of the diode when VA is 7 volts? We're going to have to calculate this. Okay, somebody tell me what the current was when we were at 7 volts applied.
$6.27.
6.27? Perfect, thank you. Okay, so we were at 6.27 milliamps. And we know our resistor was equal to 1K. And we had 7 volts applied. So, can we calculate what the apparent resistance of this diode was? Now, at 7 volts, we are above the forward voltage. However, and it should be acting like a closed switch. However, keep in mind we have a voltage drop across it, and all remaining voltage was across that resistor. So let's see what the voltage drop across the resistor was. We can figure out the voltage drop across the diode, and then we can calculate the apparent resistance of that diode. The diode is offering some resistance. It has to, because we have a voltage drop across it. We approximate it to be 0.7 volts times the current going through it, but we can get a more precise measurement or calculation in this case. So let's do 1,000 times 6.27 milliamps, 6.27 volts. Okay, let's use KVL, figure out the voltage drop across the diode. That's going to be 7 volts minus 6.27, gives us 0.73. So you can see that at 7 volts, even our forward voltage has shifted just a little bit. This is the difference between the second approximation and any approximation that comes thereafter. I guess we could call it the third approximation. Okay, so we have 0.73 volts across that, and we have 6.27 milliamps going through the diode because current is the same at every point in the series circuit. Multiply, Ohm's law. Says that resistance therefore should equal to the voltage divided by the current. So we can just take 0.73 volts, the voltage drop across the diode, divide it by 6.27 milliamps, and we should get an equivalent resistance for how this diode is currently behaving. So let's go ahead and let's do 0.73 divided by 0.00627. It is behaving like 116.4 ohms. Okay, 116.4 ohms is the answer to that. Okay, what is the approximate DC resistance of the diode when VA is 7 volts? We found that to be 116.4. We conclude from the preceding that a diode will conduct when the anode is positive with respect to the cathode, okay? So in this case, the anode, left side of the diode, must be a higher voltage than the cathode, the right side. And if we do that, it's forward biased. Okay. With the diode forward biased, measure the voltage drop across the diode for each increase in VA as shown in the observation section. With the diode forward biased, measure the voltage drop across the diode. Okay, so let's go ahead and do that real quickly. Instead of measuring current, it's beeping because I had it in milliamps. I have there we go. Okay. Measure the voltage drop across the diode for each increase in V sub A. Okay, so let's set it to 0.5. Okay, for 0.5 volts, V sub D is equal to 0.45 volts. Okay, so remember, that circuit is currently open mostly because we are below the forward voltage. If we're below the forward voltage, our diode should be not conducting. If our diode is not conducting, we measure a voltage between those 2 points because we have 0 voltage drop across the resistor. Okay, so don't fall for that trap. Okay, now let's crank that up to 1. And you get 0.55 volts. Okay, so V sub D is 0.55 volts for 1 volt. Let's crank that up to 2 volts. 0.61 volts. Okay, let's crank that up to 2 volts. Sorry, that was for 2 volts. Let's crank that up to 4 volts. 0.65. Okay, so with 4 volts applied, it looks like our forward voltage is going to stay consistent somewhere 0.65, 0.7. Okay, let's crank that up to 10 volts. 0.7. Okay, so we at 10 volts, V sub D is 0.7 volts, our forward voltage, because once it's conducting, we get that 0.7 volt drop across it the whole time. As V sub A reached a certain level of forward biasing, the voltage drop across the diode stayed about the same. Well, 0.65, 0.7. So once we exceeded that forward voltage, exactly what we would expect, we stay at that forward voltage across the diode. Okay, this implies that the resistance of the diode changed linearly, non-linearly as V sub A. Well, are we talking about it changing from before it was conducting? What do you guys think the answer should be? I mean, I would say it's non-linearly if you're including the before we exceeded that forward voltage. All right, let's go with non-linearly. Okay, this is what I don't like about some of these questions. And then so the answer would be like, well, why haven't you changed the lab? I got too much stuff to do. Okay. What was V sub D for 1? I'll let somebody else. I didn't record these values. That's on you guys. But I can reproduce it, 0.55. Okay. Okay, so that takes care of 8. I think we agreed the resistance of the diode changed non-linearly. Okay, and that actually concludes this session. Okay, so next time I'm going to go ahead and do the oscilloscope portion during the lab. And then you can fill out the rest of this on your own. So I will just do the oscilloscope portion. I'll broadcast. Actually, my oscilloscope has a web browser interface, so I can actually broadcast a very nice presentable view of my oscilloscope, much higher quality than what we would see in the lab. And you can take screenshots and use those in your lab to turn it in. All right. So hopefully, you know, there's pluses and minuses to doing this for the lab. Unfortunately, you aren't getting your hands on it. I still have no word coming back as to when. Actually, let me stop recording at this point so I don't get myself in trouble.